So, last class I have discussed the bearing capacity of layered soil, and then I was solving one example problem, and I solved case 1 when the top and the bottom both layer are considered as clay soil. So, now I started the second case, that is the top layer is a sandy soil and the bottom layer is a clay soil. So, as I have mentioned, the theory that I have discussed is applicable if the top layer is stronger than the bottom layer. That means, the top layer is a strong soil and the bottom layer is a weak soil. So, and the first case, the case 1, I have discussed that the strong top layer is a strong clay with or the I should say that the stiff clay with C value is 100 kPa, or the stronger soil with C value is the 100 kPa stronger compared to the second layer, and in the second layer the C value is considered as 40 kPa. Okay. And I got the bearing capacity of ultimate bearing capacity is 393 kilonewton per meter square. And then in the second case, that the top layer is a stronger sand layer and the bottom layer is the same soft layer with a weaker layer with a C value of 40 kPa. Okay. So, so the problem, this is the second case problem where the passive pressure we have to calculate in a different way, because we cannot put that passive pressure in the expression, that expression which is the basic expression which is developed, because in the basic expression the unit weight throughout the layer is considered as the same, but because water table effect was not considered. But in the second case problem, as the water table is considered at a depth of 1 meter below the foundation, below the ground surface. That means, it is at the base of the foundation, because our foundation base is also 1 meter below the ground surface. So, that means, this case unit weight throughout the soil is not same, because some places above the water table we have to consider the bulk unit weight, and the below the water table we have to consider the saturated or submerged unit weight. So, that is why we have to calculate this passive pressure or the force in first, then we have to put these to the equation. So, let us derive that equation first if the unit weight is not same. So, this is the case. So, the as I mentioned, this value is basically your dF by gamma into gamma b, because gamma bulk is the unit weight above the water table, which is gamma bulk, and if even the water table is not at the base, it is slightly above the base, but below the ground surface, then that gamma bulk, some portion will be the gamma bulk and some portion will be the gamma sub, okay, even if with the dF part. So, remember that, because here total dF part is the gamma bulk, that is why it is taken gamma bulk. And here the lower part, it is actually dF into gamma bulk plus gamma sub into H. Okay. So, the passive pressure, I can write that the Pp will be, or that force will be half. This I am only considering the effective overburden part, because that K already been multiplied in the general equation. I am just calculating the force. So, without considering Ka, only that overburden vertical force part I am considering, because you have to multiply with the K to get the lateral earth pressure, you know. So, that means, this will be half into h is the thickness into that because this is a trapezoidal into a plus b, and a is gamma df into gamma bulk plus df into gamma bulk plus h into gamma sub, where you know the gamma sub equal to gamma sat minus gamma w. Here the gamma w is given as 10 kilonewton per meter cube, okay, and gamma sat is 20 kilonewton per meter cube. So, gamma sub or gamma dash is 10 kilonewton per meter cube. So, I can write this equation further, half into gamma dash outside, then this half gamma dash, this will be plus 1 plus, there will be gamma bulk divided by gamma sat, then this is a part term 2 and df by h. So, this will be h square. So, what I have done? I have taken h gamma dash common. So, then this part will be your 1, then df gamma bulk plus df gamma bulk, this will be twice, okay. Then gamma bulk divided by gamma sub into df into h. But our actual equation you can see it is gamma 1, okay. So, that if there is a different unit weight or due to the water or in the soil, then we have to incorporate these effects. So, that means we have to modify these equations slightly. So, now the modified equation will be that q ultimate will be q bulk base plus gamma dash, because this is half, then this force is acting in both the directions. So, this twice into half. So, this part will cancel. So, it will be gamma dash into h square. Then if I consider the shape factor, then 1 plus b by L, then that will be 1 plus 2 gamma bulk by gamma sat into df by h into ks tan phi by 2 minus gamma dash h. Now, remember that it is this equation is applicable, it is not in general again. This equation is applicable if water table as the base of the foundation, remember that. So, now if the water table is not at the base of the foundation, it can be anywhere. Okay. For example, if the water table is here with a distance of a, okay, and this is the df. Now, this is gamma bulk, this is gamma dash. So, now what will be the pressure distribution? So, this portion it will be gamma a into gamma bulk plus df minus a into gamma dash, and this portion it will be your a gamma bulk plus df minus a gamma dash plus h into gamma dash. So, then you determine the this trapezoidal area and then multiply with the half into h, then you will get the force, because you have to multiply with the k, because that k part is already incorporated in the equation. So, that means then again you have to modify this equation that I have derived. So, the equation that I am using now is because the water table is at the base of the foundation, but if water table is at any position, then you have to modify accordingly, remember that. In the another case, suppose the water table is at below the base of the foundation. Okay. So, suppose water table is here with a distance of A, this is df, and then this portion is h. Okay. Then what would be the pressure distribution? So, this will be the pressure distribution, this one will be df into gamma bulk, and this one will be df gamma bulk plus A gamma bulk plus h minus A gamma dash. Okay. Then you have to again modify this equation, because ultimately remember that we are basically calculating the area of this trapezoidal, and the two sides A and B can be calculated in different way depending upon where the position of the water table. Okay. If there is no water, then the first equation that I have derived can be used directly, and that is, you have to do the modification if the top layer is sand, because if the top layer is sand clay, then these forces will not be required, because tan phi will be equal to 0. So, total part will be 0. So, this exercise is not required. This is required if the top layer is sand. Okay. And then remember that though, do not always use this equation for the water table case, because we have to modify the equation and we have to calculate this area depending upon where the position your water table is resting, okay, or the position of the water table. So, depending upon the condition, you have to modify this, because our case now the example problem that I have considered is where the base of water table is at the base of the foundation. So, I can use this equation, remember, very clear. Okay. So, now it is we can calculate this one, yeah, gamma df h is this is the water table, and here this is the water table. Okay. So, now first we have already calculated the gamma b, which is the clay part, and it is 261 kilonewton per meter square. Now, I will calculate the gamma top, which is this clay layer. So, gamma top will be the top layer, the initial portion. Suppose it is now resting in this soil where this is the case. So, the soil above the base level is bulk. So, I have to consider because first term will be 0, because there is no question for the top layer. So, this will be gamma bulk into df into nq 1 SQ1, because it is a rectangular footing, plus half. Now, it will be gamma sub, because your water table below the base of the foundation is submerged. So, this will be B n gamma 1 is gamma 1, and remember that again this equation will be different if the position of the water table is different. Okay. So, for example, if the position of the water table is like this, then this equation will be, for the first case, this equation will be gamma t will be A gamma bulk plus df minus A gamma sub. Okay. Then this will be NQ1, then SQ1, then plus half gamma dash B n gamma 1 into S gamma 1. Okay. Now, if this is the case of the second case, then what would be the top layer bearing capacity? If this case, the QT will be your it is the soil above the base of the foundation is gamma bulk, then this is df, then nq, sq1, then plus half, this one you consider gamma dash, because I am calculating gamma dash, then b n gamma 1 and s gamma 1. Because how you calculate the gamma dash? Because I am basically doing the same process that I have discussed during the effect of water table on bearing capacity in Tazaki's bearing capacity theory. So, that I have discussed in my one of my previous lectures. So, where I have discussed the how we can incorporate the water table effect in the Tazaki bearing capacity equation, that I am doing here. Okay. So, now because that we have to do for every bearing capacity equation if you want to incorporate the water table effect, that I have discussed, except the IS method where the water table effect is directly incorporated in the equation, you have to determine that W dash. So, now where is gamma bar? Gamma bar is equal to gamma dash plus small b. Now, if you consider this is A or B, because or you can write A itself also, no problem. So, then this will be small a, then this is b, then gamma minus gamma dash. Okay. So, now this is the general equation where b is the width of the foundation. Okay. Because now it is top layer, the total bearing capacity is resting on the top layer. So, this H part will not be there, because there is no thickness of the soil layer, because total layer is the one same layer. Okay. So, that means it will be this equation A, where A is the position of the water table below the base of the foundation. So, this way you can calculate top. So, again the QT top equation is not general for the water table case. Depending upon where your water table is located, you have to modify this equation also. Okay. So, now finally, if I now for our case, if I calculate QT, so I have to calculate this shape factor also. Now, first we take phi equal to 40 degree. Now, in such case, for measure of bearing capacity, NQ is 64.1 and N gamma is 93.7. Okay. And SC we are not calculating, because first term is 0 as phi C equal to 0. So, SQ S gamma will be 1 plus 0.1. Now, B divided by L into tan square 45 degree plus phi by 2. So, if I put 1 plus 0.1, B is equal to 2, L is equal to 3, then tan square, this is 45 degree and phi is given what? 40 degree, phi is given 40 degree. Okay. So, 40 divided by 2, that will be 20 degree. So, now this value will be 1.307. So, finally, if I calculate if on QT, then QT is coming, that gamma B is 18, DF is 1, NQ1 is 64.1, then SQ1 is 1.307 plus half, gamma dash is 20 minus 10, then B is 2, then N gamma 1 is 93.7, then the shape factor 1.307. So, it is 2732.7. So, this is the limiting value of bearing capacity of this layer soil should be within 2732.7 kilonewton per meter square. Now, we know QB. So, now we have to calculate, because I have not considered that CA part in the basic equation, because in this equation you can see there is a CA part, CA into H, because as the question is 0. So, this part will be automatically 0. So, that is why I have not considered. So, because already remember that in this equation there is a friction part and the cohesion part. So, as the cohesion is 0, that is why I have considered only the friction. And then we have to calculate the Ks. Now, to calculate the Ks, you should know Q2 by Q1. And what is the Q2? Q2, if a strip footing of width B is resting on the surface of the bottom layer, then the bearing capacity is called Q2. Now, if a strip or continuous footing resting on the surface of the top layer, when the width of the footing is B, then that is called Q1. So, it is a strip footing. If I put in the surface, so second term is 0, and the bottom layer it is cohesive soil. So, third term is also 0, only there will be first term, and that first term is NC is taken 5.14. Now, if your phi is equal to 0 degree, so NC is 5.14 as per Meyerhof table, bearing capacity factor table. So, I can see this is 5.14 C2 divided by the strip footing for the top layer is a sand. So, first term is 0, second term is 0 because it is resting on the surface. So, it will be gamma B, because why gamma, actually I should write it is also gamma bar. Okay. Gamma bar, why it is I am writing gamma bar, because in this case the water table is here at a depth of 1 meter. Okay. And for the top layer, for the bottom layer does not matter, we have to, because it is a clay soil. So, gamma is not important in this calculation, but for the top layer, suppose we are placing this foundation at the surface. Okay. So, that means water table will affect up to a depth of B from this from the base of the foundation. Here base of the foundation and the surface both are same, because it is a surface footing. So, now this is equal to B. Now, this is equal to say A. Okay. So, now we have to calculate the gamma bar value, gamma dash value, and gamma dash value is given like this. So, now if I put the gamma dash or gamma bar can be calculated like this, where A is equal to simple 1 meter and B is equal to 2 meter. So, now if I put gamma dash is 10, because gamma dash is 10, it is sat is 20 and unit weight of water is 10. So, this is kilonewton per meter cube, because this is gamma sat and this is gamma W. Okay. So, this is 10 plus A is 1, B is 2, gamma, this will be bulk, gamma bulk is 18, then gamma dash is 10. Okay. So, this value is coming out to be 14 kilonewton per meter cube for this particular case. Okay. So, that means I am writing here, this is why I am taking gamma bar, because the water table is below the base of the foundation at a distance of 1 meter from the base. Okay. So, gamma bar, and then this will be B, then N gamma 1. And why I am not taking the safe factor? Because it is strip footing. So, safe factor will be always 1. So, now this is the equation. So, if I put 15.14 C2 is 40 kilonewton per meter square, half gamma bar is 14, B is 22, and N gamma 1 is how much? N gamma 1 is 93.7. So, this is 93.7. So, this value is roughly 0.16. Okay. So, this value is roughly 0.16. Now, let us go to the chart. Now, this is 0.4, 0.2, this is 0. So, this will be 1 will be here, 0.1 will be here, 0.16 will be here. So, the chart and the phi value of the top layer is 40 degree. So, now if I draw a chart which is like this parallel to the chart. So, that means this value is around this is a 2.5. So, actually it will go further like this, because this distance is okay, something like this. So, this is 5, this is 10. So, this value is roughly 3.5. So, this value is roughly 3.5. Okay. So, this is 5, this is 10 roughly. 2.5 will be something here, it will be in between around 3.5 and so. Because it is 1.6, so it will go slightly up, so it is 3.5. So, now the 0.16, the K's value is roughly 3.5, okay, or you can take, because when you are taking values from the chart, the slightly these values may vary, because you are taking by eye estimation by your own, I am also taking. So, there may be some variation, but that is not an issue, because in your, but that variation should be very small. And in the exam problem or assignment problem, these in the exam problem definitely these K's values or the values those are required will be given in the exam problem, because required means suppose those value you have to take from the chart or those values you have to take from the tables. So, those values will be given, because you will not be allowed to take any chart or table inside the exam hall. So, in the exam problem definitely these values those you are required to take from the chart or table will be given. Okay. So, in the assignment problem also I will try to give these values, but if it is not given you can take the K's value, but the variation will not be that much significant. So, your answer and the answer that I will give will be very close, this will not be any issue. So, K's value is 3.5. So, now if I put these values, so this value will be QT. Finally, I can write that QB is what? QB is 261. QB value is how much? QB value is 261 plus your this is equation is gamma dash is 10, h square is 1, gamma dash is 10, h square is 1 into 1 plus b is 2, L is 3, then 1 plus this is 2 df by h, df is 1, h is 1, then gamma bulk by gamma dash 18 by 10 into Ks is 3.5 into tan 40 degree divided by 2, because b value is 2, minus gamma dash into h, gamma dash is 10, h equal to 1. So, this is 363 kilonewton per meter square. So, which is less than QT is fine. So, that means you can determine the ultimate bearing capacity of the layered soil if the top layer is a stronger soil and the base layer is a weaker soil, weaker clay, because that means we have discussed the two cases. So, first case is the stronger clay and the weaker clay, and then the second case is stronger sand and the weaker clay. Now, in the next class I will discuss the third case, when the stronger sand versus weaker sand. Okay. So, that is the third case that I will discuss in the next class. Thank you.